So then we can actually use the second derivative, or the concavity of a curve, to find the nature of our stationary points. Now, we already saw a few exercises ago that there's 4 different forms that a stationary point could have. Now, remember, a stationary point is just a place where the first derivative is equal to 0. In other words, it's a flat spot on the curve. So you might have a flat spot at the bottom of a trough, you might have a flat spot at the top of a hill, if you like, or you might have a flat spot where you're increasing all the time or decreasing all the time. And these flat spots are the special ones that we've already named horizontal points of inflection. So not only is the concavity changing here, but they're actual flat spots as well. Now, some important things to note. Previously, we learned how to spot one of these by saying, well, let's just investigate. We know the first derivative is 0 right here, but let's check what it is on either side. Because if it's negative on this side and positive on this side, it must be a negative turning point. And if it's positive on this side but negative on this side, it must be a maximum turning point. Now, we can still use those exact same tests, and the same tests also apply over here. Is it going from positive and staying positive, or is it going from negative and staying negative, the gradient that is? We can still use those same tests, but now we've got a new test, if you like, just an alternate test. It's another one. It's not to use instead of, but you might find a lot of the time that this is an easier test to use. What we can actually do is, instead of looking at either side of the curve, we can just look exactly at that point where we have our flat spot, and we can say, well, what's the concavity there? Because if it's concave up, I can see straight away that it's a minimum turning point, and if it's concave down, it must be a maximum turning point. So how about we just find the second derivative and see if it's positive, it'll be a smiley face shape, or if it's negative, it'll look like a frowny face, if you like. Now, it's important to note that here, because we've got a change in concavity from concave down to concave up, or vice versa, at the actual horizontal point of inflection here, what's going to happen is that the second derivative is going to equal 0 right at that point. Now, that's handy to know. If you found that y double dash equals 0, you might get excited and say, hey, that looks like an actual horizontal point of inflection, but we need to have some caution, because this is one of those rules that works in one direction and not both. So down here we have what we need a big important red box around, because this is something that we have to take note of and remember constantly. All points of inflection have the second derivative equaling 0, but not all cases where the second derivative equals 0 are points of inflection. So sometimes what you actually get is turning points that look like they're sort of disguised as points of inflection, because they'll have a spot where the second derivative is equal to 0. So you might think it's a point of inflection, it's actually not. So every time we find that the second derivative is equal to 0, it's a case where we suspect a point of inflection, but we won't be able to tell for sure unless we check for a change in concavity on either side. Because if there isn't a change in concavity, it won't be a point of inflection after all. It could be one of those ones that's sort of there to trip us up. So I'll have a look at a couple of examples that have both of those cases in them.